Welcome back to another video. In this video we're going to cover dual run capacitor basics, the things that you should know, so let's get to it. As you can clearly see here, capacitors come in two different shapes. They come in rounds and they come in oval. Bottom one there in the right hand corner is a single capacitor. It's not a dual run, and it's an oval, and it's 40 microfarad. The round one there in the middle is a dual run, 35 microfarad run capacitor for the compressor, anywhere from 5, 7.5, or 10 microfarad for the condenser fan. You'll typically encounter the round shapes in your outside condensing unit, and you'll only typically run into the oval-shaped capacitors in your air handler, assuming it's using a permanent split capacitor motor and not some electronic controlled type motor. Here's what your dual run capacitor looks like from the top. You'll have three terminals. One will be marked C. That one will always be common. You'll have an F and an H, or it could say fan and HRM. HRM means compressor, F means fan. For those that still don't understand, I've drawn in the capacitor symbols between the common, the HRM, the common, and the fan. And from common to HRM is the 35 micro part of that capacitor, and from common to fan is the 5 microfarad part. And of course, those two legs are joined together at that one point, hence that's your common point. Okay, now we're going to talk about some of the specs that's on that round-shaped dual run capacitor in the middle there. So obviously it tells you it's from Temco. It tells you it's a round motor run capacitor. It's a dual run, so it's for the fan and the compressor outside in your condensing unit. Okay, the next part is, it says 370 to 440 volts. What that basically means is how much of a voltage, AC voltage peak, can this capacitor handle. You're probably thinking, well, 370 is plenty, right? For 240 volt ACs, what you're measuring with your voltmeter? That's not what that means. When you're measuring with your voltmeter is giving you an RMS value, which means root mean squared. That's how you average a sine wave. So that is the DC equivalent of that AC voltage. Really, that voltage, if you multiply that by the square root of 2 here, that'll give you the peak values of that sine wave. And say it was 240 volts, so you stick that in and multiply it by the square root of 2, and you're going to end up with something around 340 volts. So that 370 volt is not a lot of wiggle room, but you can always go up in value on your capacitors when it comes to voltage rating. The only difference that makes is the higher the voltage rating on the capacitor just means it's larger in size. That's how that works. But you cannot go lower, because if you go lower, then it's not going to handle that voltage and bad things are going to happen. Then it'll probably blow the vent out on it. So always go higher, or at least the same, and higher is not that big of a deal if you got the room for it. Just know that if you decide to go higher, that the increased size in that capacitor means it has more cooling capacity and a higher current ripple rating value, so that equals longer life. So in this case we have a 440 volt rated AC capacitor. So just ignore that 370. That's for ignorant people that might have a 370 volt rated capacitor only, and they know that by seeing that little 370 that they know that means this capacitor will work. But all intents and purposes, this is a 440 volt rated capacitor. Okay, now we got capacitive rating, and we'll talk a little bit more about that and tolerances later in the video. Next we got ambient temperature. Basically that means that this capacitor is rated to work between -40 and 85 degrees Celsius. You convert that over to Fahrenheit if you live in the US like I do, because Celsius doesn't mean shit to me. Next we got Hertz, and the capacitors will always be rated 50/60 Hertz. It'll run no matter what. This only affects, well, if you have any kind of electronic experience, you'll know that this really only affects, the Hertz rating only affects the capacitive reactance. If you don't know what that is, don't worry about it. And under that it says no PCBs. That's some kind of like oil coolant they used to use in these, and that shit was highly cancer causing, so that hasn't been in use since the 70s, so don't worry about it. So as I discussed previously, if you want to know what your voltage peaks are in your AC waveform, all you need to do is take your voltmeter, set it to AC, measure what's coming out of the wall, and whatever number that is, that will be your VRMS, voltage root mean squared, and that's your DC equivalent. Then you need to take that number and multiply it by the square root of 2, and that will give you your voltage peaks. And then make sure your capacitors can handle those in volts. So you want to at least be, I'd say at least 80% wiggle room above that. So next on our list here is how voltage is stored in a capacitor, and obviously a lot of people don't know this, where they wouldn't be shorting across their capacitor with a damn screwdriver. So in a capacitor, voltage is stored in DC. So if you want to know if a capacitor has got voltage on it, potentially shock the shit out of you or kill you, then take your ohm meter, set it to DC volts, and measure from common to fan or common to Vrm, and it will give you a voltage reading. Let me clue you in on something. Your compressor out there in your condensing unit, this capacitor is wired in series with the start winding and the run winding in a roundabout way. And when it turns off, those two windings act as bleed resistors and take the voltage what was on this capacitor down to zero in less than a fraction of a second. So unless there's something really wrong with your compressor, this run capacitor will never have voltage on it. But to be safe, I would recommend checking it with your digital multimeter in DC volts. But you don't have to short it with a screwdriver. The one you should really be worried about if your condensing unit or compressor has a hard start kit on it. That's the one that can knock the living shit out of you, because when that potential relay or current relay opens to take that start capacitor out of the circuit, it's wired in parallel with your run capacitor. When it takes it out, it opens up, and guess what? That voltage is still there, and who knows what part of the AC waveform it cut out on. So that's the reason those capacitors, and they're always in plastic enclosures, not metal. That's the reason those have bleed resistors on them, so you don't get the shit accident knocked out of you. Duty cycle. What do you need to know about duty cycle? Well, all run caps are 100% duty cycle, and what that means is they can stay in the circuit all the time without blowing up. They have oil in them to keep them cool. The farad rating on those run caps will always be way lower than what it is on a start capacitor. And if you leave a start capacitor in the circuit for more than a second, usually if your potential relay or current relay, the contacts get welded shut or stuck on it, it will literally blow the freaking guts out of a start capacitor. And start capacitor's in there to help get the compressor up to about 70 to 80% of its run speed, and then the potential relay or current relay is supposed to open and kick that out because it has no 100% duty cycle. And plus you don't want that in there anyway, because that just causes excess current draw across the start winding. Okay, I think we've already discussed that all your run capacitors are in a metal canister with oil in them, and it helps keep them cool to extend their life. Now, next on the list is creates a phase shift. What's creating a phase shift? Well, basically from common to Vrm, placed a capacitor in series with the start winding. So what's that doing? Well, as the AC voltage builds up on that capacitor, it will get slower and slower because the charge on that capacitor is fighting the charge coming in, and what that causes is it causes the current to lead the voltage by 90 degrees. Now, is the voltage shift on that start winding now 90 degrees? No, because the winding itself has inductive reactance and you got capacitive reactance, and of course those counteract each other. So no, it's not 90 degrees. But what that does, especially when you add a hard start kit, what you're doing when you add that hard start kit is you're putting another capacitor in parallel with that run capacitor to increase capacitance. And when you increase capacitance, you're decreasing your capacitive reactance, which is another form of resistance, and that is going to allow more current through the start winding. Remember that the start winding and the run winding are in parallel with each other, so if you decrease resistance on a parallel circuit on one side, it's going to allow more current to flow through it. When you allow more current to flow through it, that winding now has a greater magnetic field, and that magnetic field is your so-called boost that people always screw up. An AC circuit doesn't work the same as DC. You're not getting a voltage boost here, folks. That AC current is just going back and forth across that capacitor. Of course, this is the reason the windings in your motor are kind of offset at a certain angle, and this is not termed as a boost. It is termed as increasing the motor's torque. Just for fun, I've included the capacitive reactance equation. As you can see, when it comes to hertz from 50 to 60, that's not going to have a whole lot of effect on your capacitive reactance. Now, the more capacitance you add to that equation decreases your capacitive reactance. And of course, the lower you make that capacitive value, then that increases your capacitive reactance. So if you want to delve more into that, I suggest you pick up a book that has AC/DC fundamentals in it. It's usually what the electrical engineering technology students take their first and second well, usually it's the first year they have that intro to DC circuits and AC circuits, and you'll cover this. But you do need to have solid algebra skills. You do need to know a bit about trig to solve this mathematically. Just for shits and giggles, probably heard the term power factor. Well, that's where this reactance comes into play. You have a true power, which is what you should be using. You have apparent power, what it's actually using, and then you have reactance power, which you don't want a whole lot of because then that increases your apparent power. And what that boils down to is you're using way more power to run that motor than is necessary, and you're running up your electric bill. Inductance motors have inductive reactance, obviously. And how do you counteract that for power factor correction? You use capacitors, and that's the reason you see certain equipment sold with a power factor correction kit, and those are capacitors, and that's how you negate that reactance and minimize your power usage. Here's a top view of the dual run. So your black there is your common, green there is your fan. And of course it does say fan on it, and then the white there is your Herm, which is hermetic. It goes to your compressor, and the green one goes to your condensing fan. And of course your black there is your common, where those two capacitors tie together. Now, I've heard a lot of people say they can just look at these capacitors and tell which is the common, fan, and Herm. That's bullshit. Now, some capacitors kind of have a standardized number of terminals on them, like common would be 4, Herm would be 3, and fan would be 2, male disconnects. Well, that's horseshit. That's not common across the entire industry, so I wouldn't go by that. Okay, you're probably wondering what this little schematic or drawing's about, and I'm going to show you how to wire dual run capacitors in parallel. That's not something you see done very often. Hell, I've never seen it done online. It's always they scrounge around in their service truck trying to find the right capacitor. And if they don't have it, well, I guess you're shit out of luck until they go to the supply store and get one, or they find something close enough to it and then they come back and change it out. But this is an easy way to come up with some really oddball capacitance values without going to the supply store. Like here, I mean, this would be an oddball one. Like say your compressor required a 70 microfarad capacitor and say the condenser fan required a 10. You might have the 10 microfarad maybe, but you sure as shit probably don't have that 70. That's kind of an odd size, or an 80. So you can wire like I said, 235.5 capacitance dual run capacitors and get those values fairly easy. Now say if you needed just a 70 and a 5 microfarad for the fan, well, you just don't hook the fan terminals up in parallel. So what we're doing is we're coming off a T1, which is one side of our hot leg, and of course that goes to both commons on both capacitors. Of course that feeds the Herm and the fan caps on both of them. And then what we're doing is we're coming from the fan up at the top, and we're jumpering the fan terminals together, and then we're going to jumper the Herm terminals together, and that puts them in parallel, so the values add up. So then we end up with a fan at 10 microfarad and a Herm at 70 microfarad. And it's real simple. Now if you just need a 5 microfarad for the fan, you just don't jumper the fans. You'll have an extra terminal open on the dual run. And also this setup here will last a hell of a lot longer than a single run cap, because the cooling capacity is greater and the current ripple rating value is much higher. So and at the end here where it says fan 10 and Herm 70, those points there would be where your start windings hook up, and of course your run windings would hook to T1 or the commons on those capacitors, and then of course your commons for the motors would hook to T2 for the other side. What we're doing here is we're verifying the capacitor value, and according to the capacitor it's listed at 35 microfarad plus or minus 5%. Now what that means is you need to take 35 and multiply that by 0.05, and that will give you a 1.75. Then you just add 1.75 to that 35 and you get the upper limit value, and then if you subtract 1.75 from that value, then you get the lower limit. And as long as your capacitive value reading falls in between those two, the low and the high, then your capacitor is deemed good. So as you can see, both common to Herm and the common to fan both fall in the correct range, so our run capacitor is good. Alright, we're ready to wire these two capacitors up in parallel and get our 70-10 values that we want. Now, you can watch the schematic up in the top right corner there, and it's going to draw out what we're hooking up in the correct collar, and we're just going to hook it up. I'm not going to talk because you're probably tired of listening to me, so we're just going to wire this up, and at the end you'll see that we get the values that we need. And we're just going to jumper the commons together, we're going to jumper the fan terminals together, and we're going to jumper the Herms together, and that's it. It's real simple, but you very rarely ever see this being done. Alright, I'm going to jump back in here, and what we're doing right here is we've uncoupled the fans. We're no longer jumping them parallel, and we just want 5 microfarads. So you just hook your fan start wire up to one of those, and you get your 5 microfarad that way. Here I'm going to show you how I hook them up in series. Is there a practical application for this? Not that I know of, because the commons are tied together. Sort of just throws this out the window. If the commons weren't common and they had their own separate terminal, then you could probably use this somehow, but practically, no, there's no real application for this. But I do want to show you, if you wire them in series and they're equal value, what that does to that value. It always chops that much directly in half. At the end of this video, I'm going to show you the math that's involved in this with parallel and series capacitors. Stick around for that and show you some quick shortcut equations. Okay, hopefully you stuck around to the end of the video here for the math, and we'll start with the first one, the parallel capacitors. That's the easiest one, as you can see in the picture there, that CT is equal to C1, that's capacitor 1 plus capacitor 2 plus capacitor 3, and etc. So you're just adding the values up. Sadly, the education system in the US sucks ass, so I'm going to go over some basic math so you understand what I'm doing with the equations when it comes to series capacitors. So what we have right here is 3/7 plus 5/6. And if you don't remember what parts of the fraction are, I'll go over that. The top number is the numerator, and then the bottom number is the denominator. So 3 is a numerator, 7 is a denominator, 5 is a numerator, 6 is a denominator. So we cannot add fractions unless the denominator, the bottom numbers, are the same. And the easiest way to do that is to multiply 7 times 6, and our denominator will be 42. But when you do that, you're multiplying like 3/7. You're multiplying by 6 over 6. We're not really changing the value of that number. You're multiplying by 1, so 6 over 6 is 1. Then we go to 5/6, and we're multiplying by 7 over 7. And that's how that works. So you're not really changing the values. You're just making those numbers to where the denominator will be the same, and then we can add the top parts. So from there out, you should be able to figure it out. And if you can't, please go out, find a hammer, and smash yourself in the head and do the world a favor. Hopefully you stuck around after the basic math and adding fractions and it scare you away. So now we're on to series capacitors. Now the equation for that is 1 over C, the capacitance total, equals 1 over C1, capacitor 1, plus 1 over C2 plus 1 over C3, and indefinite how many ever capacitors you got. And from here on, I'll show you how to manipulate the equation. Okay, we're going to start off with something simple here, just a 2 capacitor circuit. Alright, for a 2 capacitor circuit, you've probably seen this equation before and probably wondered where the hell it come from. This is exactly how you derive this equation. C total, or capacitance total, equals C1 times C2 divided by C1 plus C2. Basically, you're starting off up here with the general equation you got for just 2 capacitors, and then you find a common denominator, which is going to be C1 times C2, right? If you don't understand that, go back to the basic addition for fractions part of this video. And remember, C2 over C2 is basically like multiplying that part of the that value by 1, and then C1 over C1, same type, it's same shit, folks. It's not that hard. Then you end up with C1 over or 1 over C total equals C1 plus C2 over C1 times C2. And to solve for C1, you just take the inverse of both sides. That flips both sides, and then that ends up being capacitance total equals C1 times C2 divided by C1 plus C2. Now this is an easy, quick equation to remember. If you just got 2 capacitors in parallel with each other, and you can come up with the answer really quick without using a calculator. Well, you'd probably want to use a calculator anyway, but this is one of the shortcut equations you can use. Does it work for like a 3 capacitor circuit? Yeah, it does, according to some people. Like over at Electrician U, that apparently can't do just general math. Yeah, you can make this a 3, derive the equation for 3 capacitors, and I'll show you that here. Here's our 3 capacitor circuit, and those are the values that we're going to use. And now I'm going to derive the equation for that 3 capacitor circuit, the same as I did for the 2. Okay, here's the equation, same as before, just an extra capacitor. Like the previous equation, we need to find a common denominator, and then we multiply the top accordingly. I've isolated, that in red, so it's easily visible what I'm doing here. And would I do this in the real world? Hell no. Once you go beyond 2, this equation gets highly complicated, and you're more likely to make a mistake. So then that's where I use a calculator, and I'll show you how to input that stuff here in a second. this is the calculator method, and if you've never seen this done before, that -1 power, if you type in 2 to the -1 power, you're going to get an answer of 0.5. And the reason you're getting that is that -1 means it's really 1/2. So that's what this means. So when you're typing this into your calculator, you'll type in 10 to the -1 power plus 15 to the -1 power plus 5 to the -1 power. And that will give you an answer. But your equation is still 1 over CT, so you need to take the inverse of that answer to get the true answer for CT, and that will give you 2.73 microfarad, just as we got from the previous equation, but a whole lot less complicated and a hell of a lot faster. Also, before I leave you, when I said about the capacitor voltage rating, you want to size that to where your voltage rating is maybe 80% or less. So, and another rule of thumb is you want to size your capacitor voltage rating wise to like 1.5 times the size of your actual voltage peak. So I'll leave it at that, and hopefully you learned something in this video, and later.